So I think what we'll do is spend a little bit of time maybe looking at a couple more animations that are available on visualphysics.org. I want to go through the number theory stuff and then get a sense from you guys which one of the other things we go through, because you got to get your what number theory looks like correct. I think it's important. So one of the most important things is that real numbers are boring in terms of animations. So real numbers, so we've got a minus real number and two positive real numbers, and they always are at the origin. Okay, so maybe it's going up there. Blink, a little bit of dot, and now blink, 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 blink. And they never move left, they never move right. These things are parallel. And there's kind of a very funny, I think it's funny, personal story connected. Okay, so I'm becoming this expert in determinism. Okay, so what's the value of that? Okay, so I'm unemployed for like a year. Okay, how would everything make it down? A friend of mine says to a friend of his that I'm going to do through school, and he says, I'm looking for smart guys. So this guy actually drives up to see me. And this was in a time when absolutely nobody had GPS that people had. I don't know why. And he's one of these guys who's designing financial models of things. You know, deals with very large amounts of cash, and all you have to do is take a slice, a little bit of sliver of that, and that's a lot of money for you personally. And so we're having this little discussion. We totally out of job. And him totally connected to making a lot of money. You know, you start with six figures, but it's the bonus you really want. Okay. And he said, oh, so you do your own thing? I said, yeah, I'm going to attorney. Get a first attorney? And he's like, no. And he's like, that is successful. And then I said, well, how about complex numbers? I'm sure if you're building these financial models, you know, complex numbers will come in there and say, never get it. Oh man, my expertise is so irrelevant to you. And it is. And it's, to me, it's this profound fun that come out financial markets. They only care about these thoroughly boring. But remember what I'm doing. I'm treating these as events in space-time. I'm treating the real numbers as time. And so that old thing about time is money, okay? Time is money is boring. Whatever. It's kind of a fun little connection. All right, so real numbers, in terms of animation, don't look so great. But how about complex numbers? Well, complex numbers, they can move. They can move, which is good. But they move in straight lines. And you know, if I didn't use, you know, X, Y, and Z formula like this, and use thetas and whatnot, they move in curved lines, however you define it. But basically, it also is kind of soft. Less soft, but still a little bit soft. Now, formally, the next one is addition, but we've done that twice already. And this is one of these ones that just surprises me, even to this day. I'm going to animate norms. Okay, so the yellow is the input. Okay, it's a bunch of different values, and then I do a reflection in space. Okay, so I see pairs. Remember how you have the pairs of things, and then the norm. Well, the norm has an x of 0, a y of 0, a z of 0. So it sits the origin. Okay, so I've always thought of norm as how big something is. When you animate everything you do, then your norm is how old it is. Here's my norm is actually big. But that's a different perspective, isn't it? And does that bother you 30%? Okay, it's like now norm, I can't think of I got 5%. I think that's good enough.
cool little observation.
How did you make that insight of going from size to animation?
This animation? No, I got to tell you, this is the honest truth. The one animation I figured out ahead of time was the determining position. I said that's going to be moving along the straight line, no problem. Every other one of these, almost without fail, I said, I kind of look, no, whatever I bet on is wrong. It's like my intuition failed me over and over again. And I made this thing isn't moving at all. And it's like, yeah, norms are never, ever, ever. So that's another fun thing. This is going to be fun walking around and going, why does that make sense? It shouldn't, but it does. And particularly when you look at the pile of numbers.
I should let me do one other thing about these things.
Because the norm is nothing more. You still feel norm is by except by writing things to
no, it's in essence it's a message from the math. The math says, okay, take a number with three vectors and a scalar, do its mirror, multiply the two together, and all of those come together to just give you a scalar. Scalar, no pointiness at all. Okay? And that pointiness in an animation ends up being how old it is.
By pointiness you mean direction.
Yes.
Vector.
Yes.
So it's vectorness free. Okay. So each one of these, by the way, I represent several different ways. I'm focusing on these things which have three complex planes, the animation, the superposition, and a random sampling of the superposition. And then I know our brains really don't like motion, and so I have these kind of smaller ways of representing them. This is the actual command right there that created this process. So when I say it's a little user unfriendly, but at least it's readable. That's what it took to actually make it. This let's see, iPod. I actually did that. I usually try and include the math that I was actually using, and there are the actual numbers. So that's why I say that it's so amusing to see this endless pile of numbers and say, oh, I'm going to make a film out of this. I'm going to make a film and I'm going to think about it. Its philosophical implications. It's like, really? Okay. So let's go back. All right, so let's take a look at some polynomials. Okay. So here's a second order polynomial, and
this is also a great example of why I use a complex plane. The complex plane is just that scalar with a t or a c with an x or a y or a z. It's because when I say I want to see a second order polynomial, I want to see something that's got a vector. This yellow is the input. That's what I'm putting in, and I get the red thing out of it, and it's got the vector thing. I like that. Okay.
Let's see. Is this animation? Have I crashed my computer? Is my computer getting confused? These are all GIF animations, which is not a really fancy technology, but it was one I could figure out how to, program in.
What do you use when you get the animator? You just use the stack.
I could just make what is it? 100 frames. I do 100 frames with one day.
So you actually write the animated GIF file. Yeah. You don't use the animated GIF program.
So I want to see the hooky thing. Okay? Now, the hooky thing is in the animation, but somehow never quite looks at it. So there's a little red dot, really around, okay? If there's a hook going on, it doesn't feel right. I always feel more comfortable with the static image
that shows up in the complex plane. Let's get to things that are even more fun. Let's go to a third order one. So this can have a curve to it. Let's see how long it takes it to. I better close down the things going on. Hopefully, it won't get too confusing. It's really having trouble. All right, I want to simplify some other things. No, I better keep.
Looking at running a browser?
Yeah, no, it's just a browser. We're at the website visualphysics, and we're in the quaternion animation section.
Yes, important fact. The yellow is always, I shouldn't say always, usually the input. Okay? So, I could, in fact, if I don't go through the words and things, usually get even more confusing. Okay? And then this is the polynomial. And if I look down lower, I see that it is q to the 3 minus 2q plus 4, something like that. Okay? And that feels right in these complex graphs. But look at how crazy this is. Okay, this red dot. We get one red dot. Oh, now we have 3 red dots. Now we have 1 dot. Okay, and
Is it 3 inputs?
no, I took this input and I created a polynomial out of it. I got a pile of determinants. And that pile of determinants works like this red block. And what this does basically is it's doing this, and at this point, there is, and I'm going to use some language from quantum filter, there's a creation event. And the creation event has 2 particles go like this. Okay? And then, when we get to here, we use that regarding quantum filter, annihilation event, okay? And what's like really crazy, attractive, I can't quite reach there yet, is that those words in the quantum field theory stuff, I mean, they teach you how to use that in the keywords. They certainly never show you a picture, okay? And they certainly are of this opinion that there will never, ever be a picture of it, okay? And I'm starting to think that, no, those are good words. There are possible animations out there describing. So that's what this feels like. I mean, this looks, and the complex thing is very simple. And then when I look at it in the animation, I see a creation event, I see an annihilation.
It's going to feel very analogy.
Oh, yes. Yeah, we talk about, this operator won't create, particles in these states.
But you have textbooks with stickers, right?
Exactly. And my big dream that could only possibly do, I have on this or other days, that there will be a picture of every single one of those things. And this is the first kind of glimmer of that kind of thing. Because I certainly, when I just do the program, here's how I'm going to make my program thing. And I got the command that it's ugly, okay, and I didn't expect it to be seriously.
If you started from the quaternions out of the math,
yes.
You aren't starting from the physics. Where did the physics?
No, that's day 2. You missed day 2. Okay. So day 2 is really hard. No, day 2 is quantum field theory of phrases, just written with quaternion machinery. And I should say it was just written. At this point, Brush worked very different, except maybe there might be more phases to it. But a lot of it is just dead on the standard stuff.
Let's see if we got. So let's just jump. Yeah, there are variations on this. Let's see what happens all the way down at the bottom here. Yeah, it quickly becomes so confusing that didn't I make this animation? It was like,
yes, and I don't quite understand. Oh, this is the yellow and the red. Okay, this is what the yellow and the red, they go together. Okay, and that's what we just spent so much time trying to figure out what's going on with creating an annihilation. And all I did was I started at the same spot. I just didn't go through the order. Remember how I said I like going through yours and I get less degrees? I get more degrees by just taking exactly the same out of those. Okay? Just convince what it goes through yours, and it ends up creating an orange one. So now I don't have that icing flexing sort of thing. I need this graph job, you know, changing over here. So what is it's like, no wonder we live in such a wonderfully simple, in-depth, confusing world. It's all the mathematics that take out. I guess like now I've got a good feeling for what's going on.
I'll have to look at the together so I can get that.
I don't understand.
I understand the math that I used down below here. Let's see if I've got that summarized nicely right now. Let's see with the... okay, so it's just Q3 plus 3Q minus 2. And in one case, I go from minus 3, minus 3, minus 3, plus 2, plus 2, plus 2, plus 2. That would be the yellow and the red combination. And now, if all I do is go to a different point, I start the same thought. I understand. And it's like, well, that doesn't look too complicated. But it does look, like the one you said that it wasn't like, this is connected to something deep in the universe. It wasn't.
So unlike nanobodies, it took me a very long time to get dinosaurs. But at some point, you began to get a little bit of a feel for how the given equation created this pattern of analysis.
Yeah.
Okay. And in fact, they eventually turned it into a product by having dropdowns, particularly, and so on.
Yeah.
So, are you at a point now where you really don't, you have a feel for when you do a polynomial and so on, what it's going to unfold into? Have you gotten any guidelines?
I think I'm too much an experimentalist, and my experimental attitude is to say, is this important? Okay, if this is important, I want to not put any bias into what I want it to look like. I want to make sure I'm testing it right. And so that's why there's maybe 7 or 8 different polynomials to get a feel for some of the important parameters around it. And I just been too wrong in what the final thing looks like.
Is there any way, a possibility of automating your experimentation where you would, you come in very easy, you build something that's great, whatever you do. The other end would be something that would have a way of looking at the resulting images and saying this has the characteristics to make it interesting.
Well,
you can then do billions of things.
Well, there is just an enormous mountain of software development that could go into this. But I have so many balls up in the air, and it's a fight over what I do next. And I thought about maybe taking a mathematical class to, let's do this in Mathematica, because that has far more reach than these tools that I have. I know Mathematica, quote unquote, can do all this stuff, but it's quote unquote, because to me it's important to have all 6 of those things together to get a sense, to get the sense that I've got the complex things because that looks like I expected to look. The animations and super conditions. It could have all be done. I just haven't made the investment that direction. I decided to go so that or develop the website so it has no reach.
These kinds of things. Fair question. All right. Yes, it's not dealing well with all these animations. Okay, so I guess let me try and do just two more. I'll try to explain these box sort of thing, and then we'll look a little bit into the science because that's let's kill these pages. Kill the pages. Let's see if let's open up good old Firefox and see if Firefox does a better job. That's going to be the. No. That's going to be the live Stand-Up Physicist live episode. So, all right. So these are basically, at this point, these are all the animations that I've made, and this is a 3 spatial dimension and 1 time dimension wire cube. Okay. What is this thing? Oh, that's the one. All right, so this is what a 3 spatial dimension and 1 time dimension cube looks like. And again, I programmed it. I did that solid the program to do. These are the numbers. This is what it looks like. So if you're a little confused now, that's okay. It's traveling, it's cubing with 4 degrees of freedom. Has 16 points. So 1, 2, 3, 4, 5, 6, 7, 8, 16 points. 16 versions. Okay? And in any cube in the box, what you're basically doing is saying, I'm going to just change one parameter in order to get over here. And then I'm going to change one parameter in this case y to get up to here. Okay? But since we now have time, I'm going to go from in time. That's what's going in there. We're traveling in time up to the next 3D solid spatial, next to 3D sphere. Okay. So this is -1. Oh, we're not at -1 anymore. We're traveling to +1. We're traveling to +1 where I can show you the wire cube. So that's what travel through time looks like. And formally, yeah, that's what happens. You see the collection of numbers and you go, oh, look, I've got -1 in the time column, and I see my x's, y's, and z's all changes per thing. And then you see the t, x, y, and z all three, and we put the time part that's changing, and that's what most of the video is traveling from one, what I would call a wire cube, to the next.
In your view, is the piece of time already in existence and then leading back to the present with that
I see this is a 10-second universe. Actually, I make it a little larger than 10 seconds. It depends on how big the box is. I work with volumes of space-time, okay? And the volume of space-time is a little bit later than linear. Okay, that's why it starts with nothing and then you see the rate. Okay? So I see this as the formal definition of a cube, which is to think about starting at -1, and just writing all those, okay? And then saying, let's go from here to there, that's literally, this is Z, so this would be E along like that. Right? And just doing that whole process. And the ones that go like this is say +1, +1 to -1, -1. The one that is like that, that's one of the dots that appears predominant in animation. Okay? So I'm looking really formally and going from here to here versus from here to here because this is the scale, this is the timeline that's fitting. And so to get this
so then does your stuff work just as well if one looks backwards in time?
Yeah, usually that's
okay, so then the notion of forward backward in time is nothing special about going backward in time.
No,
I think it's interesting. one of the few places where classical colors.
I would have to take a pretty long digression about this, but that is an important issue. And the reason, in my opinion, it's not handled correctly is because you couldn't think about it as a problem of time. No. That's the arrow time problem in connected entropy. Believe me, a lot of people have spent a lot of effort on it. And I think it's just a poorly formed question. You have to think about space-time. Okay? Space-time has a function. It's the space part of space-time that has a function. And if you do it that way, then that problem is varying. Well, it's not that it's not that. It's like, I'm trying to make the point about poorly formed questions. Poorly formed questions can never be answered. What does 1 plus equal? I hope I don't get that on the test. I will never be able to answer it. And what is the arrow of time? I don't think it's going to ever be answered. And believe me, people, really smartest people on the planet, have thought about it. They haven't come up with the answer. And I don't think they ever will. But what is the arrow of space-time? And what is the consequences of including space when you start to do that analysis? That, I think, will go very far. But that's one of these subjects that I actually have a very solid first step in, and have never taken the subsequent steps. And there are a huge number of subsequent steps to take. Actually, it was on the board yesterday, but since you asked the question, there is this thing called the density, okay? And very, very importantly, when you say what element do you need to take an event A and go into the time. Make it C. So all the things with its time. And the element, the density is simply minus 1, 1, 1, 1, 0, 0, 0. Great. So you go, what would it take to take half and go back? I bet it's the same thing. You can play ping pong forever, okay? You play your ping pong forever, play a billion times, nothing matters, okay? That, in some ways, is what their problem is that they're doing. And they're not going to solve it, in my opinion. Okay? But they're right. That is a problem. It is a well-defined problem. All right. So what happens if you say A is a determinant, and I'm going to use my big reverser die, and in order to get to B, okay? It's a well, you can do that. Okay? But what if you wanted to go the other direction? Would you have an R die over here that would be would you just take the same darn thing? And in order to get back here. And the thing is that there's a cross product, okay? Well, I know people have said bad things about that cross product. But that cross product turns out to be wonderful. Because if you deal with, in classical physics, the cross product that shows up in pulling off these operations, and we're not talking gradient surgery as far as the objects, we're leaving that data. But the cross product here would be, in a classical situation, really ridiculously super tiny. Okay? So tiny that this thing approximates just being like -1. Right? Because you say, I don't have any care about the vector part of the A die, and so just take it -1, and I'll go back and forth. Okay? I'll go back and forth. Except for this little residual little cross product die that's never the same when I go back and forth. So if you do that 100 billion times, okay, that cross product starts to matter. And it's that cross product nature, I think, that makes the that we see every day show up. Okay? But you have to abandon the little.
Adding up of those little insignificant terms.
Yes. Yes.
So it's like you have a Taylor series, and you say, oh, you throw away the D and DD2. You just throw it away. That's one way. The other way is also, you can just put in the A, and the arrow. Somehow along the line, something
That's a fancy thing. That's a fancy thing. But I'm saying it's non-fancy. It's just that time is so much bigger than the space part. Okay? That this is almost like 1. This is almost like -1. And so that flips it around. Okay, so Quaternion-wise, I have lambda approximately equals just -1, 0. 0 is everything. Okay? That's what my kind of duty was. And it's just like, but it's not quite, because this will have a vector. This will have a vector. And if those have little vectors in them, then only those little bit of differences. And when I say little, I mean, you literally have to go over like 10 digits, before it shows up. So 10 digits, I'll forget about that, the thermal doesn't.
What does it correspond to physically? In a sense, noise.
The space part. Yeah.
Is this in a sense related to virtual particle? Is this in a sense related to nothing?
Not it. But the thing is, so I have that little observation that, the cross product matrix, but there's so much to thermodynamics, and I haven't connected that little observation to any concrete equation. Okay, in advanced equations, like in equation 2, I haven't made that, look at my reversal thing, and look at this law of thermodynamics. That's a long march to make when I have equations.
These are the things that do add up. What do we manifest that?
The asymmetry seen in nature, which is, that nature is not reversible on a large scale.
You have to get into the kind of asymmetry you see on particles and antiparticles?
I haven't done it.
All right, so I wanted to give you that sense, and I wanted to do one other thing with sines and cosines, because sines and cosines are just so important to how the world works, and they just don't look right, at least in my hands. There we go. Trig functions. Okay. So what here we go. These are,
let's see, the yellow input, let's see, I haven't looked at this in a while. They have to do with surf. So I fixed the x, the y, and z. Okay. But the blue one is pointing kind of in a different angle in three-dimensional space than the red one. The red one is commonly pointed in different space. And they have different amplitudes. Sine functions you can multiply out big numbers or small numbers. Who makes it small? But they kind of go to different places. So that's.
Let's see. Sines and cosines. So maybe I should look at what the equation I'm really dealing with is here. Oh, it's not showing up. Darn.
Why do you like sines and cosines?
Well, I'll tell you why. Because I've been taught, everyone's been taught the same thing. It's like sine looks like this, and cosine looks like this. Okay, that wasn't very accurate to God. But the million components of the planet. And I started playing with things, and I did this thing to take goes from -5 to yellow as usual is my input. It goes from -5 to +5, and I said, okay, go from -5 to +5, type it into Q sine, type it into Q cosine, showing my million damage. And I didn't see this. And even to this day, I don't quite get what's going on. But,
what do you mean by million damage?
That's what I expect to see when I do the thing. And here, well, everybody everybody's kind of in the same, on the same line. So that's one thing that happens. When you deal with sines and cosines, the polynomials that point in the same direction, and so they will always have this, we're on the same line to this. But, you know, if you force me to say, well, which one is the sine, which one is the cosine, I think I get that wrong about half the time. Because I haven't gotten comfortable yet with this stuff.
You're really dealing with sines and cosines as you would any other function.
Yes, it's just a function.
Just a function, rather than going back to say something like vibrational equal stuff and saying analytic wave equation.
Yeah.
You're together with you.
I just expected to see something like that, and it wasn't even close.
And so what I did to make this one
was I made the changes in time much greater than the changes in space. And when you do that, you get these nice spirals. In the complex plane, if everybody of you thinks it's just a continual glory, like, oh, spirals in the complex plane, and then you look at the animation and you go, where are those spirals? I mean, they're there, okay? It's the same collections of numbers that are used to make every single point of these things. And you can see why I'm going to have trouble communicating with Dr. White, anybody, even myself. Because there's not a sense of, oh, we've gotten slowed down. Well, I guess you could focus on one dot and say, well, he's now speeding up and he's going to class and he's going to break. So actually, if I focus on that red guy, he's kind of hanging out, he's going to decrease speed, and he's going to crash into somebody sometime. Oh, there we go. So if you isolate one guy, you can sometimes make a transition between what's going on in the complex plane and what's going on over here. But, you know, as I said, I didn't know what to expect when I was increasing changing time relative to the thing of space, and you know, this kind of thing. And you just go, the kind of possibilities that happen with this staggering, you go, well, I'm not even filling up space. I'm just filling up the line, you know? These animations, I guess we really say, okay, it's still about space, but let's just fill up a line. Really?
I would think that it would just have more spirals. That's my guess. Yes. Tighter spiral. Yes. Yeah, we got some. All right, so, and this is just signs in many different directions. So this was born out of the frustration of not really
filling up space-time very much. And so I just basically chose different values of the three vector parts, the x, y, and z. And so that way, it never looked as crowded in the animation. That's what happens when you start filling space. It makes kind of looking on the
So let me just make a couple more points about the website itself. So we've got manifestos, which are supposed to be my overall attitude, tutorials, which hopefully explain how things work. The animation section, which goes through these different maths that I've figured out so far. The downloads has the software that I've gotten to work on Macs, PCs, and Linux boxes. The preprint server is my own preprint server. They're all of 7 pages here, 7 articles. They're web viewable. In other words, you don't have to download and print the PDF. You can go ahead and just read it here. One of the more unusual aspects is that there is also a Mathematica notebook because you can be very light and be skeptical of my math skills. And this is my internal check to say that I am providing well-formed math is the idea. And then the new thing is the talks page, which will have all of these, which has day 1 here, day 2, and the PDF of this talk. Although this is more spontaneous than that. The forums is a place to chat, and as I pointed out, I think on day 1, it's basically Doug chatting at this point. It's not a community. We do have, I should say, I think the amount of people asking me about this stuff around the globe is manageable at this point in my life. And so I usually will get back to you in relatively short order if you decide to ask me any question as well. And we are definitely, this is definitely a global endeavor. I know some people in Bangalore were excited about this stuff. But then here are all the notes, and there's somebody else who's not on this continent who couldn't be in Boston, and but as I said, we're going to be so it really does have global reach, and that's really kind of cool about it.
How many people know mandatory these days?
Oh, I get an email couple times a week. That sort of thing.
So how many people do you think in this community that really represent the involvement or understanding? There isn't a community. Or I haven't tapped into there are people who do flip it out because they have an active community and they have a meeting once every 2 years. I went to that once and they said, oh, well, you're just a small section of flip it out. Oh. All right, so I think we'll end it there.
Girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
It's my favorite thing out of this whole thing of the Stand-Up Physicist is just the sound of a mic, thing coming through the amp. That doesn't belong in a classroom, does it? Okay, so I need my clicker. How can I do the top of the clicker? All right. So first you'll notice that picture. It actually is not very good, but I am the MIT T guy. When you go through Tyndall Square, there are these two nerds, about 19 years old. One of them holding up a little dish. Actually, they're both holding up a little dish. One's got these teardrop glasses and a nerd watch. That's me. Okay. I am the face of MIT. I hated that photo. It showed up in Tech Talk, and it's been up there for now decades. And so I am the face. But let's go through the 10 slams, top 10 slams. Let's see what they are. All right, so the first slam is theoretical physics grants me too many experiences in humility. Oh. Inflation, the search for a new constant velocity solution for gravity. I don't think Guth would really summarize it that way, but that's that's my own take on it. Dark matter, the search for a new constant velocity solution for gravity. Okay, very similar. And again, I don't think people who do dark matter research would think that was a slam at all. No, that's just nonsense. All right, the future moves, get with the program, analytic animations. That's what you suffered through. Oh no, that's what you enjoyed today. All right. 6. Wrong ideas can be made arbitrarily complex. See work on strings. and hopefully none of those people are in my audience and will come hurt me later. Okay. The brightest people on the planet cannot explain the simplest shit because time screws with everything. Maybe. All right. Black hole math is bogus. If that works out, that there will be more than a few people who are not happy. So I think a lot of people think that comment is bogus. General relativity, good but wrong. Oh boy, we're not going to be popular with that one. God plays with the norms of derivatives. And that was in the second day talk, that claim. And the final thing, I don't need no stinking Higgs. And that is on the t-shirt. So thank you all very much.